Questions about anything last time, about anything? So last time I talked about this heat problem, one-dimensional heat problem. So the problem was a one-dimensional hot wire. The hot wire is not radiating any heat sideways. So there's the hot wire. It goes from 0 to L on the x-axis. And I'm holding it at 0 degrees at the left end point. And at the right end point. So that's like slapping on refrigerators to hold the temperature at 0 degrees. And then the famous problem is that this is modeled by the heat equation. So there's a PdE, du dt, equal a constant, positive constant. It's not the speed of light in this case, it's constant that comes from the heat properties of the material. And let's see, that the boundary conditions are that U of 0 for all time is held at 0, that's the temperature, and U at the right end point is held at 0 for all time. So those are the boundary conditions. This is the PdE. And then we know the temperature at the beginning, at time 0. So that's the initial condition. So at time 0, we know the temperature is given by something, and it's a function of f of x given. That's the initial condition. Okay, and that f of x is given. Interesting thing to consider is I'm going to show you a solution to the problem where the initial temperature on both sides is 0. So that would make sense. But you could also have the temperature not be 0 and kind of like slap on refrigerators at time 0 and see what happens when your left and right temperatures don't start out as 0. And we'll find out pretty clearly what happens in that case. U of x at time 0, sorry, thank you. Oops. Yeah, so that'll be interesting. So I want to review what we did last time. I did the method of separation last time and found the solution that U of xt by the method of separation of variables is the sum from n from 1 to infinity coefficients bn e to the minus c. Here's a very interesting thing, n pi over L squared. So that's a huge negative number because of the n squareds and the in there, and and e to the minus something big is something really small. So that's going to help that convergence of whatever this series dramatically times sine n pi x over L. That's the solution I got. I guess I'll put that in the box. Where those b's are the Fourier sine coefficients. And when you don't have 0 to pi, they look very similar. Instead of being 2 over pi, they're 2 over L. Integral from 0 to L of the function times the basic orthogonal functions, which in this case are n pi x over L dx. Okay, and I thought I'd demonstrate using Maple 2 problems. let's see, I want to do one problem where the initial temperature is just our harpsichord pluck shape, since we studied that so in depth. So we have 0 here and L here, and that's the harpsichord pluck shape. That's a fun one. Another interesting, we studied the Fourier, well, let's see. We've actually studied the Fourier sine series for the function 1. I maybe didn't mention that at the time, but the function that's just 1 from 0 to L. So that would be a case where we heat up this wire, and then at time 0, we slap on refrigerators. That's going to be interesting to see what happens in that case. And I claim, I guess I never wrote down the Fourier sine series for that, but if I extended it as an odd function, the Fourier series for that step, that's our unit jump function, our quintessential jump function. And it has only sine terms in the series because it's an odd function. So we actually know the sine series for that function, which is 1 from 0 to L. Okay, so now I'm going to switch over to Maple. Show you this. Oh, blast. Okay, I'll have to do this. Where's Maple? There it is. Let me make it bigger. 3. Is that big enough? Can you see that? Okay, back there? Too small? 4. That's bigger. Okay, I'll start pushing return. The first command loads a bunch of programs that aren't automatically in Maple. There they all are, a whole bunch of great things when it comes to plotting functions and even in 3D. But I want to animate this solution, so animate is the command I'm excited about adding. And if you don't want to see all that junk, you can turn that semicolon into a colon. Then it loads all that stuff and doesn't tell you what it loaded. Okay, let's see. We calculated the Fourier series for the harpsichord pluck. And remember, it was the coefficients were 1, 3, 5, 7, etc. And they alternated between being plus and minus. And it was like 1 over 1 squared, minus 1 over 3 squared, plus 1 over 5 squared, etc. times the corresponding sine functions. Anyway, that's what we got. And the 4 over pi is just a constant that comes out in the front. Okay, and I've convinced you probably that this really does converge. So there, I'm going to post this afterwards in case you want to experiment it with yourself. But I've graphed this before. The plot really does converge to a peak-shaped pluck shape. And let's see, how many terms did I go? I went out 20 terms, and that's counting like 1, 3, 5, 7, 20 of those, all the way out to, let's see, that would be 39. 2 times 20 minus 1. So that's a lot of terms. It's probably overkill. Okay, let's see. Notice that I have the solution to the heat problem here. That exponential term is in there. Otherwise, it would just look like the sine series for the function. But now it's got an e to the minus 2 times n minus 1 squared t. And I took L to be pi. Makes it simpler to look at. And I took the c to be 1. Okay, so there's that. Now let's animate it. This is kind of cool. Let me slow it way down. Let's see, I click on it. Frames per second. I want to get it really kind of, let's do 2 frames. How about 1 frame per second? Yeah. Oops. Okay, ready? I slap on the refrigerators and let the heat start getting sucked out of this thing. And so you see that it very rapidly sucks out the heat. If you stuck your hand in a refrigerator, it would cool rather rapidly. An interesting thing I promised was that, let me play it again. Notice that it has that kink in the beginning. And then whammo, right away, it smooths that kink out. So that's a very interesting thing about the heat equation. If you have a singularity like that kink, it instantly goes away. No more singularity. That's a feature of the heat equation. Whereas for the wave equation, that kink propagates. Remember, we had those traveling waves, and the kink actually would split into two kinks, and they'd go in opposite directions. That's a feature of the wave equation. The singularities propagate. And a fascinating thing, I could let this thing go, and it would look like zero pretty quick because those exponential terms die away so fast. But of course, the temperature is never totally zero on the inside. It goes to zero incredibly fast, but is never actually totally zero. Questions about that? Now, a fun thing to do is the other problem I promised. Let's see. So this is the Fourier. These are the Fourier sine coefficients for the classic jump function. And remember, they don't alternate anymore, but they're only the odd functions, the odd numbers. So they go 1, 3, 5, but they're not square integrables. So that was one of the features that was weird about that, and they don't alternate. And that Fourier series convergence is a lot more subtle because of that. There's the function. Now I want to plot it. You've seen this plot before. It has the Gibbs phenomenon. And even with that, that's 20, so that goes out to 39 in the denominator. Even with that number of terms, it doesn't converge nearly as nicely as the harpsichord kink. Okay, well, now I want to animate what happens to that heat problem. Let's see, is that going to animate it? Notice I have number of points 100. When I didn't put that there, it looked really crummy up at there. In fact, it still looks kind of crummy, but adding a number of points 100 means there's a number of 100 points in the animation, in the x variable. Anyway, I'm going to push play here. I'll do a slow, no, I want frames per second 1. Okay, let's animate that. Where did it go? Doggone it. 1. Okay, I see. I can't do that. Sorry, I'll fix this. 1. Okay, now I'm going to push the animation. Go. Once again, all the weirdness gets smoothed out. There wasn't really any weirdness up there, but it got smoothed out. And another interesting thing that happens is that the temperature at the endpoints, of course, it goes suddenly down to 0. Bang. So when you slap on the refrigerators, the spot close to 0 and pi suddenly goes down to 0 in a kind of a singular way. But every place else is real smooth. And that annoying junk at the top, the wiggly stuff, that's not really there. But that's just a feature of Fourier series that you can't get rid of that ugliness at the edges. I could add more and more points and make the ugliness closer and closer to 0 and pi, but I just can't escape that ugly Gibbs phenomenon. And that's just a feature of my sum solution. It's not a feature of the actual solution. The actual solution would be 1 and then suddenly smooth out and go down to 0 at 0 and pi.
Since
Still says 10? Wow. Maybe I'll try pushing enter. Now it's nice and slow, drippy. Yeah, so that's what it does. And it's like in the beginning there, it's like a bang. That's going a long time now. Okay, so I'll do it again. Bang. It smooths out. The temperature on the ends streaks down to 0, etc. I thought I'd show you something fun you can do with maple here. Now I'm going to take a function of two variables, s of x and n, and that'll be I'll show you that's the same function, that's the same sine series converging to the function that's just 1. And it goes out to n, but now I make n a parameter, okay? And I want to graph the Heaviside function on the same graph. The Heaviside function is 0 to the left of the origin and 1 to the right. So our function that that's minus 1 to the left and plus 1 to the right is 2 times the Heaviside function minus 1. Okay, now I'm going to make a sequence out of those Fourier series. So they would be the nth partial sums as n goes from, how about 5 to 11? Did I plot it? Oh, I did. Yeah, I defined it above. So I plotted a sequence of those things. And notice the jump, the Gibbs phenomenon jumps, gets pushed farther and farther out to the edges. And if I took even more, you'd see that it got squeezed in there even more. And it's fun putting all these partial sums from the first 5 terms to the first 11 terms. You kind of see a secondary Gibbs phenomenon. So it overshoots by the same amount. That's sort of a fixed overshooting amount. That's the Gibbs phenomenon. The second bump seems to also overshoot by a fixed amount. And those all get pushed out farther and farther as you take more terms in the series. But it's pretty slow, crummy convergence. And that's why Fourier series are of limited use when you get into these spots. It gives you a valid solution very rapidly. If you wait a couple seconds, it'll be very accurate. But these singular things cause problems, at least in the short term there. And if you're desperate to get a beautiful formula for that solution, you'd be out of luck. You have to use more subtle kinds of analysis if you really want it to be accurate there. But it's accurate after a couple seconds, it's very accurate. And you can verify that by doing experiments. Let's see, that's the Fourier series on the positive. If I can do the same thing on the interval from minus pi to pi, and of course it looks like that. They all go through 0 because that's the midpoint of the jump. And it looks like that. Questions about that or about maple? That's a fun thing to look at. Okay. Sorry. Okay. There's the two solutions. I thought it would be a worthwhile thing to do to derive the heat equation, because that's a classic thing to understand, especially if you're going to go do science and engineering with the math you've been learning. And this is also going to show you that some of the math you've been learning is important. So how to derive the heat equation. Stein does it, but he does the infinitesimal version. which is worth reading about. So he takes a little delta x. This is x. He takes a little x, and he takes an x plus delta x, and he analyzes heat flow coming in and out of a little delta x thing. I like to do the control volume method. Actually, in the case of a one-dimensional heat, it's not a control volume, it's a control length. That's the method I'm going to use. Okay, so the control volume method is going to be, we're going to look at a piece of the wire that starts at x1 and goes to x2. And think about the physics of the heat in that piece of the wire. Okay, so an important thing to know is the meaning of the word calorie. 1 calorie, this was invented by Lord Kelvin, is the amount of heat or energy. It's the amount of heat energy required to raise 1 gram of water 1 degree centigrade. To raise, that's 1 cubic milliliter. 1 gram of water, 1 degree Celsius, or Kelvin. That's the same thing as Kelvin. The only difference between Kelvin degrees and Celsius degrees is where 0 occurs. In Kelvin, it's absolute 0. In Celsius, it's the freezing point of water. So, using Kelvin's idea, the heat, whatever that means, in this interval from x1 to x2, that would be some constant depending on the material. That's the heat capacity. But it would be an integral of x1 to x2 of the temperature. This is going to be a function of t now, dx. Okay. The hotter the thing is, the more heat it contains. And the heat it contains is proportional to the temperature. So I'm adding up little delta x's there and saying, okay, that little delta x is temperature something. That contains the number of degrees times the some constant. Okay, that's the heat in there. And now the rate it changes, of course, is equal to d by dt of that. At k times that integral. And you think, well, if everything's okay, I can differentiate under the integral sign in that other variable. This is an integral with respect to x, and I'm differentiating with respect to t. So that would be a du dt. Think of a difference quotient you'd write, and you'd look at it and say, oh yeah, as long as everything's converging nicely, I can differentiate under the integral sign. Okay, that's basics physics. Now I'm going to tell you what Kelvin's law is. Kelvin's law is that the heat flow is proportional to the temperature gradient. So let's say it's cold on this side. This is the cold side, and this is the hot side. Let's see, I'm going to go from cold. Let's do green to yellow to orange to red. Okay, let's think of the way the heat would flow. If that's the hot side, the heat would flow this way. It flows from hot to cold. All right. And if you think of the temperature gradient, the derivative of the temperature would be going in the other direction. This is the temperature gradient or derivative. Okay. And Kelvin's brilliant conjecture, which he verified by experiment, is that if it's super hot, the heat flows fast, and if those are close in temperature, the heat would flow slow. And he convinced himself that the rate that heat flows is proportional to the temperature gradient. So heat flow, the rate of heat flow, is proportional to the temperature gradient. But notice that it points in the opposite direction. And so it's important that there be a minus sign here, because it goes the other direction. If that temperature gradient was gigantic, the heat would be flowing really rapidly to the left, the opposite direction. Okay, to get ready for the next step here, I'm going to draw a graph. Here's an example. Here's my x1 and x2. I want my temperature gradients to be positive here. So here's my temperature. I've got a positive derivative over here and a positive derivative over here. So let's see. The hot side on that one is to the right, and the hot side on this one, let me make it a little bit more convex. Okay. Okay, those temperature gradients are positive, and the flow here, because it's hot to the right and cold to the left, the heat flow would be going in. But on this side, it's hot to the right and and cold to the left, the heat flow would be going out, even though they're the same directions. So here the flow is going in, and here the flow is going out. Okay, so now I'm ready to do something. The rate of change of the heat energy in x1, x2, I got two ways to write it. One is as the integral from x1 to x2. Let's see, there was a k there. du dt of xt dx. And that's also equal to, okay, so heat doesn't go anywhere. The only way that heat is changing is is either flowing in to the right or at the left or the right. They're either going in or out at the left or the right. That's the only thing that's changing the amount of heat in the content in that interval. So, and those, let's see, the one on the right is a constant times the temperature gradient, which is just the derivative of the temperature at x2 dt. Okay, and that's flowing in, so that's a positive contribution, right? If that du dx is positive, then it's flowing in, and that's a positive contribution. But on the other side, if that derivative is positive, it's actually flowing out. So that's why this is a minus c du dx at the other endpoint, x1t. And somehow I've got to relate this to the heat equation. And the key here is to realize, aha, I can write this as an integral like on the left if I think about the fundamental theorem of calculus. So that would be the integral from x1 to x2 of the second derivative. Okay, you're starting to see the heat equation, d2 dx squared. The fundamental theorem of calculus would spit out du dx, the antiderivative, at the endpoint x2 minus the same thing at the x1. So that's just the fundamental theorem of calculus. And now how fascinating. I see the heat equation. I'll put it all under one integral, and I'll put it all on one side. Integral from x1 to x2 of k du dt minus c d2u dx squared, integrating with respect to x. And that's a big fat zero. Okay, and that's why I call this thing a control volume. x1 and x2 could be anything. So the aha, x1 and x2 can be anything. If there was a moment in time and an x where that thing was strictly positive, so let's say the graph at some moment looks like this. And it's positive, let's say, in this case it's positive right here. So u of x naught, t naught, is a positive thing. If that were to ever happen, well, what would I do? I would pick my x1 and x2 close enough here. Actually, this is what I want to be positive. I should call this something. What would you call that? Phi of xt. If that were ever strictly positive, or strictly not zero, I could put an x1, x2 like that, so that integral would not be zero. I would get that the integral from x1 to x2 is not equal to zero. So because that is that thing integrates to zero no matter what the x1 and x2 is, we conclude that that thing inside the integral has to be the zero function. So we conclude this thing is identically 0. And so when you solve for du dt, you get C over K. That number would depend on the heat conductivity or the heat capacity, et cetera, et cetera. One of them is a rate. That's the one that's the conductivity. And one is the capacity. So if you're going to do thermodynamics, you'd have to think hard about that kind of stuff. And of course, all the different materials have different constants. That's how you derive the heat equation. That's my favorite way to derive it. I think it's fascinating to think about how you would do a similar thing in 3 dimensions. Let's do the 3D version. In this case, the thing is really a control volume. Okay, so I'd get this blob, 3-dimensional blob. I'd call that my control volume. And then I think about the heat content. Let's see. I'd have here let's have a temperature gradient. That would be the gradient of the temperature. That's the temperature gradient. And there'd be a normal vector here. If the temperature gradient is flowing along the surface, then of course it's not exiting. The heat's not exiting. It's just flowing along the surface. So the case when you get the most efficient flow is when that gradient is pointing in the normal direction. And so let's see. When I do the same routine here, I would get the rate of heat flow, the rate of change of the heat, in V. Okay, that would be d by dt of the heat content, which would be a triple integral this time over the volume of u of xt d volume. And so that rate of change would have to equal to the net heat flow. That heat is either going in or out. Net heat flow. And when you start thinking about those kind of things, you realize that that's equal to, but using Kelvin's law on an infinitesimal, let's see, the surface here would be an S. That's the surface of V. This would be the integral about the surface of that would be a 2D integral, and it would be the gradient of U dotted with the normal vector times the element of area. And if you kind of think about heat flow like fluid flow, you think of a little cylinder of heat popping out. This is called the flux of that vector field, the flux of the vector field grad U. And now this is a moment where Gauss's law comes into practice, or the divergence theorem. So the divergence theorem would say that that flux is equal to, constant just floats along, and you get the triple integral over V, and you get the divergence of the gradient of U dV. And of course the divergence of the gradient of U is the Laplacian. And so when you do this game with the control volume in 3 dimensions, you get the integral over the solid volume. When I put that derivative underneath the integral sign, I would get k times du dt, and here I'd get minus c times the Laplacian d volume. And you conclude by exactly the same reasoning that this must be 0 because the control volume is arbitrary. If you found a spot where it wasn't 0, you'd make a little ball go in that little spot and show that, oops, that couldn't possibly be 0. I guess I find those arguments more satisfying than the infinitesimal versions, where you take a little delta xyz and think about heat flow across all the boundaries. It's kind of messy. Yes. So because that's 0 for any old control volume, the thing inside must be 0. Let's see. Oh, now in this week's homework, there's something to think about. Other heat problems. The homogeneous boundary conditions that we've been studying means you slap on refrigerators. Oh, by the way, if you do this in 2D, you get green. You see why Green's theorem is so important. The homogeneous boundary conditions corresponding to slap-on refrigerators to bring the boundary down to 0 degrees. Another interesting case is the insulated end. So let's see, if it's insulated, it means there's no heat flowing. So no heat flowing if it's insulated. So by Kelvin's law, the temperature gradient would have to be 0. And in the one-dimensional case, so let's say that would mean d by dx at LT. du by dx at LT is equal to 0 for all t. That would be the right hand, that's the right-hand side is insulated. That's a pretty interesting problem, and it leads to Sturm-Liouville problems that involve different kinds of boundary conditions. And that's one of the problems you've got in your homework. So the first problem is both ends are insulated. And then the second problem was related to one end being insulated. Those are interesting to think about. And it's also interesting to think about what happens. For example, if I start out with the harpsichord shape pluck, if the ends are insulated, then you would expect the heat not to go away. It can't escape. So what would happen is the temperature would equalize. And guess what the limiting temperature is going to be? Take a wild guess, yeah. Exactly, right. And you can demonstrate that using the Fourier series techniques. So if you slap on insulation on both ends, that pluck shape would equalize and spread the temperature out. And of course, in the limit, it would be constant. And that constant would be the average of the pluck shape in the limit. That's what you would guess. Let's see, another possible thing to study, which is pretty interesting, is radiative boundary condition. So if you're out in space and you got a hot something, infrared heat radiation would send off that energy out in space, and you'd cool off. So if you're stuck in a space capsule and it's not insulated, you're going to get really cold really fast. Anyway, that one is that the heat is, let's see, what is it? Let's think about the radiative heat condition at L. The amount that radiation, so let's see, du dx, that's the temperature gradient. If that's positive, that means the left side is cold. Let's say it's negative. That would make, if that temp gradient is negative, that would mean, let me draw for my own thinking here. There's the temperature. That would mean that that's negative. What does that mean? Yeah, I think this is a negative. It's minus C times U at LT. So let's say it's really hot, then of course the temperature, the heat would flow to the right. So the temperature would have to be, is that how you think about it? Let's say U is really hot. Then the heat would be radiating, which should make the gradient negative. I believe I'm thinking correctly. I sat through a lot of classes where they were trying to teach me this stuff. I was an engineering undergraduate, so I had to take classes on this stuff to make sense. And I think that makes sense. If this was really hot, then of course it would radiate a lot of heat. And if it's radiating a lot of heat, that would have to make, by Kelvin's law, the gradient negative. So, and of course that C would depend on how much is allowed to radiate. If you have a substance that doesn't radiate very well, like a black wire, okay, good thing I'm running out of time. I didn't think that, I'm not going to test you on this or make you do anything with it. I just wanted you to be exposed to it. Because sometimes in a math book, it's really disappointing to see them derive a physical problem. That's really an important thing to do, called mathematical modeling. It's actually a really